So now we're going to think about, well, what if I have a 3 by 3 or higher matrix? How do we do that, right? 2 by 2 isn't that bad. It was basically just the first part of finding the inverse of a 2 by 2 matrix and then calling it a day, right, and solving for it. But we can't really do that because there's no actual equation for 3 by 3 or higher inverses. So for that, we're going to call it something called the determinant. And I always said this because in my head it's the same thing, but I'm not really sure why he introduces it so late in his book, but it's still understandable. This is the only time we really get to use it, but I guess it's good to know the very beginning when we talk about inverses and stuff like that. Just find a determinant because it's basically the same thing, which is the nice part. But let's officially give its definition. So let A be a 2 by 2 matrix, this portion. The determinant of A, denoted as d of t of A, is equal to that. Now again, if you notice, right, this is the same thing as just the inverse. For the inverse of a 2 by 2 matrix is always 1 over d times A times d minus c times b. And then again, they get the matrix of that portion, but this is the main problem, right? If this is 0, therefore it's singular. If it's not, it's non-singular, right? That was the big thing. And in fact, this number right here is actually very important. It's called a determinant of A. Okay, so for a 3 by 3 matrix, again, there's no proper way of doing it. This gets a little trickier and messier. It's not as simple as this itself, but there's a way to break stuff down. Okay, so for a 3 by 3 matrix of this format, the determinant of A is equal to the actual coefficients of the entire first row times the determinant of each one individually. Like that. So I always say, for example, A is here. So if I just eliminate row 1 and column 1, you get this matrix there. In the middle, same thing. If I eliminate row 1 and now column 2, this entire thing, what's left over is this matrix here. And then lastly, the same for C. Get rid of this portion and then get rid of that column. You are left with that. And then from there, we get the determinant of a 2 by 2. So in other words, we're back to square 1. So if you're wondering for a 4 by 4, well, that means we have to go through this process first, then to that process. So eventually, you just get back down to a 2 by 2 determinant. But using this process, and one thing you got to be careful of, it's always plus, minus, plus. So the minus is always in the middle, and the 2 pluses are on the outside for this 3 by 3 matrix. Okay. So now that we actually defined it, and we've been using it for a while already, let's actually find the determinant. Okay. You'll see why this is actually pretty important. So find the determinant of each matrix. So this is a nice one, just crisscross subtraction. So negative 4 times 2 is negative 8, minus 1 times 2 is 2. So we just get negative 10. So now using our new 3 by 3 formula here, so the determinant of B is going to be the first entire row is going to be the numbers in front. So 1 times this determinant of, I'm just going to put determinant, but the matrix itself of 3, 1, 1, 4. So we'll get the determinant of this. Minus, so according to rule, it's always minus middle term, so 2. And then determinant of now is going to be 0, negative 2, 1, and 4. Again, the determinant of this. Plus a negative 1 times the determinant of the last one. So you just cross this off. 0, negative 2, 3, and 1. Okay. And now we just slowly break each one individually. So it'll be 1 times 12 minus 1 minus 2 times 0 minus a negative 2, and then minus 1 times 0 minus a negative 6. Okay, so this gives me 11. This is a positive 2, so negative 4 when you multiply that by that. And this gives you a positive 6, but it's going to be negative there, so it gives you that. So we end up being just 1. All that for just 1. Okay. Right, so there's got to be a reason why we're doing the determinants, because remember, the whole problem is the eigenvalue problem. And we only did 2 by 2s, and that wasn't that bad. So the whole, again, the goal is to find any type of eigenvalue and any type of eigenvector, right? And this is a start. At least we got it from 2 by 2. How does the determinant help us get a 3 by 3 eigenvalue and a vector, right? And unfortunately, this is going to be about the same process here. A little snippet is eventually going to be doing that. And again, that breaks it down arbitrarily, give or take. Okay. All right, but we go any further. There's actually a very interesting topic because, again, everything helps us to find that individual problem, right? So something called minors and cofactors. Okay, so a minor matrix is the elimination of a row and a column. The resulting matrix is called the minor matrix of A. Okay, now we've actually already done this. We're just calling it now what it represents, and each of these here are called the minor matrices of A, because according to what it says, if I eliminate a row, which I did, eliminate the entire row, and a column, which I also did, this is now the minor matrix. So we've been doing that already. Right? Now we're just calling it something that's actual proper term. So therefore, let's do notation. So definition. Let A be an n by n matrix, then the n minus 1 times n minus 1 matrix resulting from removing the rth row and the nth column from A is called the minor matrix of A and is designated by that notation. So it's MRS, where the RS is the actual row and column you actually take away or you eliminate. Okay. So let's try some examples out using our new definition. So find the minor matrices M11, M23, M34 of the matrix A. Okay. So according to the definition, all this is saying to find minor matrix 1, 1. And you could put a comma if you like, or you guys tell, because there's no way we're going to have 11 columns and 11 rows, right? So you could think it's 1, 1 is pencil. I'm going to eliminate. Remember, it's always row by column, and that same process applies here. So first row and first column. So essentially, the first process of getting the determinant, and you'll see that in a little bit. So this is the minor matrix 4, 6, 1, negative 1, 3, negative 2, 2, 1, 3. And we keep going in the same process. So next one is 2, 3, or just 23. So again, that means so second row, third column. Like that. So the cross is right there now. Whatever's left over, I plug in here in the exact same order I see it in. So literally, basically, think of it as just skipping an entire row here, an entire column here. Just like that. And then the last one, M34. So third row, fourth column. And there we go. Not bad, right? So if we go back to our definition of our 3 by 3 matrix and getting this determinant, which is that equation there. Well, again, right, we can technically replace, like I said, these are all minor matrices with its proper notation, let's just say. Okay? And its proper notation actually is right here. So if I want to rewrite this using no more matrices and using the minor matrix notation, well, this A value is the first is in the first row in the first column, so that's why it's A11, times this determinant, which is just the minor matrix getting rid of this row and this column, okay, minus the second value here, which is again in the first row in the second column, times the determinant. Well, that means if I get rid of this and this, that's this in this matrix, which again is just the first row, second column, plus third entry, which is the first row, third column, times the determinant. Well, you cross this out, it's the minor matrix 1, 3. So again, just another way to write using actual minor matrices format. Okay. So the question now becomes, what if I asked you to find the determinant of a 4 by 4 matrix? Can you just rewrite the actual equation you would use to break this apart using this type of pattern? Okay. So the determinant of this 4 by 4 matrix A would be, well, if you notice again, it's always the first values themselves. Okay. So it'll be A11 times the determinant of the minor matrix of M11 minus the second value in the second column times, again, the determinant of the exact same minor matrix. And we keep going in the exact same pattern. There we go. Okay. All right, so next part of it is something called cofactor expansion. Okay, so now the sign of a minor matrix alternates from positive to negative. And that's always going to be the case. So if I do a 5, I'll do positive, negative, positive, negative, positive. But if it's 6, I would do positive, negative, positive, negative, positive, and then another negative. I would end in the negative part. Okay, so it just alternates sign at every single part of this expansion. Okay, so now the question becomes, these sign minors are called the cofactors. So the actual sign, so like the positive, negative, are called the cofactors of the minor matrices. Okay. Now this is an interesting part because now I can pickpocket however I choose, and because any minor matrix I want to deal with, right, including this one, right, this is just this portion, so I could find the sign of this minor matrix without actually having to do every single step and seeing if it's an odd or even type of situation. Okay, so that's what this comes into play. Okay. So cofactor expansion. So this is the determinant of a matrix with respect to row or column. Okay, so again, figure out what the actual sign change would be or the sign value would be. Okay, now it's actually pretty straightforward. It's kind of nice. It's a very nice, easy equation to remember. So given a sign change of the Ij component, this is going to be the value of the sign change. So it's -1 to the addition of the two column / row operations. So for example, if I go up here and I want to figure out what sign change would be, what would the determinant be here of the sign change, I would add these two numbers up. So 3 plus 4 equals 7. So -1 to the 7 power is negative. So therefore the cofactor would be negative for this minor matrix. Now, again, why do we care too much about this? Okay, so again, it just helps us understand higher matrices. It's just as simple as just a 2 by 2. So again, for example, so given a 3 by 3 matrix, the cofactor expansion along with the second row would be what? Okay. So again, so I want just the second row. So if I just go to, let's say, for example, 3 by 3, I'm getting rid of the entire second row. So I would do the same exact situation if I want to find the determinant of a 3 by 3, but instead of using the first row expansion, I'll use a second row expansion. So the only thing will change, well, these will be 6, 3, and 1 now. Oh, sorry, 6, 3, and 1 now instead of 4, -1, and 2. Okay, so that's what this represents, something called the expansion of the cofactors at a given minor matrix. So let's see how this would work out. So this would be, well, let's just go the general term first. So this would be A21 times the determinant of the minor matrix of the exact situation. And we'll talk about the sign changes in a little bit. So A22 times the determinant of the minor matrix, 2, 2. And then A23 times this determinant. Again, just following along there. Right? So now we got to figure out the sign changes at each individual step. So that's where this equation comes back into play. Right? So the ij component is just addition of these two. So 2 plus 1 is 3. So it's odd, so it's going to be a negative sign. And from there, you actually don't have to do the rest because it's just alternate sign. So there we go. And you can do that for any arbitrary one you like as well. Right? It doesn't even have to be 2, 1. It can be 2, 3. So it just limits this one in the first row. Right? So it gets a little bit complicated and pretty interesting when it comes to it. So, for example, given the matrix A, find the third row and first column cofactor expansion. All right, so third column, third row. So let's go to the third row, which is right here. All right, so this is going to be, I'll do the general one first, and I'll just plug in the numbers after that. So third row, so A31, determinant of M31. And again, I'll do the sign changes later. A32, and then A33 times the same determinant. All right, so now the sign changes. So 3 plus 1 is 4, so it's positive. Or it's even, actually. It's even. So we know those are the sign differences. Okay. Now, that's the expansion, but let's go a little farther. What if we want the actual determinant, right? So if I just rewrite this, so well, this is kind of nice. And if I just go through the process of just getting the determinant, right, so keep going and breaking this down, I end up getting this. As the determinant. Okay. Now, like everything else, there's a reason for this madness, right? Okay, so now let's do the same thing, but now for the first column cofactor expansion. So again, that means the first column, so now it's all of this, is going to be the A's themselves. Okay, so let's just take our time. So this is going to be A11, right? That's the first term. Determinant of the same minor matrix. Okay. Now this is represented as, okay, second row, first column. Okay. Last one here is so as third row, first column. And a random space there. Okay. All right, so 1 plus 1 is 2, so even, minus, plus. Okay. And again, we've finished the expansion, but let's actually find the matrix, or not the determinant, just like we did here, for example. So rewriting this will be -1, yeah, this, okay, yeah. Got a little off track there. There we go. Which, again, gives us this. Wasn't that interesting? We get the same determinant. So the question now becomes, does it matter how I get the determinant? Or in other words, do I have to use the first row, or can I use, well, any row or any column? And that's a nice thing. So now we get the actual definition of an arbitrary determinant of an n by n matrix. The A be an n by n matrix, the determinant of A is a number, the determinant of A, given by this equation. I guess I shouldn't do that. I should cross this out. It's not really proper math. Is given by, I should put this given by, probably better English, this. Where again, the jth component can change however I choose. Okay. But again, as we go later on, you'll see this actually isn't the complete case, because there's alternatives now. It's very interesting how we got the same determinant and we used completely different things, right? But this is our general term, right, for any n by n matrix itself. Okay. So therefore, if I want to find the determinant of this 4 by 4 matrix, which is horrible to look at, right? So again, you think of it as just breaking it down. So you go by 4 by 4 down to 3 by 3 down to 2 by 2, right, with something that's easy to do. Okay. All right, so to find the determinant, you could do multiple ways, right? You can do the expansion of the entire portion. So it's going to be 1 times the determinant of this now 3 by 3 matrix, or cut that off. Okay, minus, again, these are all determinants, right? Plus, minus, minus. I'll just do that. And again, if you notice now, it even breaks down even more, right? So now we go back down to 2 by 2 and do the same process, right? So, oof, becomes a complete horrible mess. Or you could just take my word for it, and this ends up being 67 at the very end. So, a couple nice theorems applied here because of that is this is not fun to do. It's got to be at least somewhat of a nicer way to do this. Okay. So, a couple things before we get to the main one at the end is just like determinants or just like inverses, transpositions, and all that. When we ask to find the determinant of two matrices multiplied, the same thing as finding each one individually and then multiplying the results together. And the nice one is, given an n by n matrix, A is singular if and only if the determinant equals 0. So that means here comes our eigenvalue problem, right? So that connects the determinant to the eigenvalues and eigenvectors. And then the major one, which is pretty nice actually, is let A be an n by n matrix with minor matrices I, j, and cofactors of that. Then the determinant of A is equal to any sum of any row expansion or any column expansion. Now the reason why that's fun, because sometimes one is much easier to do than the other, right? Instead of just brute forcing your way of just doing always the first row, if there's a bunch of zeros somewhere, like for example here, right? So this is nice. H gives you less work to do, right? That determinant is going to be identically the same. So meaning instead of using this row itself, if I use the second row, in other words, my first one will be A21, A22, A23, and A24 instead of A1, A2, A11, A2, A2, A13, and 14, I get the same result. And because it's 0 here, that entire minor matrix determinant ends up being 0 as well, which means I have actually less work to do at that point. So in that case, that's why this is really nice, because, you know, a lot of times it's a lot easier to do stuff when it comes to it, right? And again, that's what I say here.